Alright, these series of videos will be on entropy, which is chapter 6 in our textbook. And we're going to be looking first at the inequality of Clausius. Okay, so we've been talking about cycles, and whenever a system undergoes a complete cycle, Clausius's inequality says that the integral of dq over t over that entire cycle will always be less than or equal to 0. And it's possible to prove this for all cycles, but it's a lot easier and equally instructive, at least as instructive, maybe more so, to look at just a simple single cycle that operates between two temperatures. So of the nature of the cycles that we've been drawing for our engines and refrigerators. So first let's look at the case of a totally reversible engine. So dq over t for the cycle is only going to happen at the high temperature and the low temperature. So it's q of h over t of h plus q of l over t of l. But for a reversible system, q of h over q of l, since one is in and one is out, is equal to negative t of h over t of l. And so if I make that substitution up here, I end up with something that's equal to 0, indicating that for any reversible cycle, I'm going to have exactly 0 for this cyclic integral. So what happens in the case of irreversible? Well, if we select a system where the q of h is the same whether it's done reversibly or irreversibly, but now attach a cycle to it, one is reversible, one is irreversible. The thermal efficiency of the reversible will be greater, which indicates that the work produced by that engine would also be greater. If you play the little game of W net equals Q net, okay, then Q net for the reversible is larger than Q net for the irreversible, indicating that the temperature or the low temperature heat loss is going to be greater for the irreversible than it was for the reversible. Plug that in, knowing that for the reversible case we got exactly 0, now we get something that's negative. So anytime I get negative for my cycle, this is going to be irreversible. And this is one way of testing whether something is reversible or irreversible, or if it were positive, I would know I had something that was impossible. So next we want to define entropy. Entropy is sort of an odd little critter. It's a property of a system, but it's defined in terms of an imaginary process, not even a real process. I think that's what disturbs people about it. But we define it based on how much change there would be to heat transfer at a particular temperature if it were done reversibly. And this will give me a change in entropy. Now, I can imagine a reversible process, I just can't build one. But that means that I can calculate it based on these imagined processes and get answers that are independent of the actual process of getting there. So that's actually more useful than it sounds like it's going to be. Now, what I want you to really look at this point, though, is a couple of things. One is that the units on this has energy units divided by temperature units. Okay? That's going to be really important for us to remember as we're doing this, that the units are not just energy units. Entropy is energy divided by temperature. Then also, since it's defined for a process, for a change, we always had that plus C when we integrate, right? You always had to add that integration constant. So there's a basis, some arbitrary starting point, which we define to be 0. Since it could be anything, we're going to just have to accept that the table chose something and was consistent in using that same starting value for all possible data points that they tabulate in the data book. This also means, however, that one data book may make a different selection than a different data book, so you've got to be careful as you jump from one table to another. Our final section in this video is about how you're going to find that data. The good news is S, or entropy, is just exactly, in terms of patterns, the same as V, U, and H. So it's the last column in our data tables. We had volume and we had our internal energy and enthalpy. And there was this weird column S over to the side. S is our entropy values. We're going to use it in the same way that it's going to increase as I go from being a liquid to saturated liquid vapor mixture to a superheated vapor. And so I can use all the same rules for calculating it, including using it for quality, knowing whether or not it's superheated, etc. So in terms of finding data, this is going to be a piece of cake. If we've learned how to already read the other numbers, we can read these numbers. So we're going to pause the video here, and we will start back up and begin looking at some special processes.